Hello, let's work through the problems assigned out of section 6.2. So first up, we are given a point, P, which is expressly given to us as being on the unit circle. Okay, so if I draw my standard coordinate axes here and I draw the circle of radius 1, so this has radius 1, in other words, x squared plus y squared equals 1. The center is at the origin, 0, 0. If I have a point on this circle and it's given by negative 3/7, comma, 2 root 10 over 7, so I'm in quadrant 2, I have a negative x coordinate and a positive y coordinate. I'm not trying to draw this extremely accurately, just vaguely accurately. I'm in the right quadrant at least. So the point is negative 3/7, comma, 2 root 10 over 7. Corresponding to t, meaning measured from the positive x-axis going in a counterclockwise direction, that's the angle t. Okay? So what we are asked to do is we're asked to find the 6 trigonometric functions of t, namely the sine of t, the cosine of t, the tangent of t. These are our 3 standard functions. And then the cosecant of t, the secant of t, and the cotangent of t. All of these functions are defined in terms of the x and y coordinates of the corresponding point on the unit circle, and thankfully we were given them. The sine of t is the y coordinate, the cosine of t is the x coordinate, the tangent of t is the ratio of y to x. The cosecant of t is 1 over the y coordinate, the secant of t is 1 over the x coordinate, and the cotangent of t is the ratio of x to y. So we just have to refer to the point we were given, where y is 2 root 10 over 7, and x was negative 3/7. So those right there give us our sine and cosine. And then we can take these values and start constructing everything else. So for example, our tangent is y over x, 2 root 10 over 7 over negative 3/7. I can cancel my common denominator of 7 for negative 2 root 10 over 3. My cosecant is 1 over y, so I just need to reciprocate. Instead of 2 root 10 over 7, it's 7 over 2 root 10. And if you are particularly averse to having radicals in the denominator, if I multiply top and bottom by root 10, we get 7 root 10 over 20. The secant is the reciprocal of the x coordinate, so instead of negative 3/7, I'll have negative 7/3, nothing to simplify there. And the cotangent is the ratio of x to y, so it's negative 3/7 over 2 root 10 over 7. I can cancel that common denominator of 7 for negative 3 over 2 root 10. And if you don't want radicals in the denominator, multiply by root 10 over root 10 to get negative 3 root 10 over 20. And there we have it. We found all 6 trigonometric functions of t. So next we have a very similar problem. We are given a point on the unit circle. Notice that both coordinates are positive, so I'm somewhere in the first quadrant. Okay, so here's my unit circle. My point is somewhere in this quadrant. The x coordinate is 2 root 30 over 11, and the y coordinate is 1 over 11. The angle is therefore from the x-axis in the counterclockwise direction, so this angle here is t. The sine of t is the y coordinate, which is exactly 1 over 11. The cosine of t is the x coordinate, which is exactly 2 root 30 over 11. These were just given to us. The tangent of t is y over x, which is 1 over 11 over 2 root 30 over 11. Cancel the common denominator of 11 for 1 over 2 root 30. If you don't like radicals in the denominator, root 30 over 60. Next, we'll have, for example, the cosecant of t. That's 1 over the y coordinate, which is just 11. The secant of t is 1 over the x coordinate. That's 11 over 2 root 30. I'm just reciprocating them. If you don't want radicals in the denominator, you can go ahead and call this 11 root 30 over 60. And finally, the cotangent of t is x over y, which is 2 root 30 over 11 over 1 over 11. Go ahead and cancel your denominator of 11 for just 2 root 30. So having done this once, doing it another time was pretty quick. Moving on. Find the exact value of the cosine of 6 pi. So what we need to do is we need to start with our unit circle and then beginning from the positive x-axis, we rotate in the counterclockwise direction until we've marked off an angle of 6 pi. So remember that going all the way around the circle is 2 pi. So if I go all the way around the circle, now I have an angle of 2 pi, but that's not enough. I keep going. I go all the way around again. Now I have an angle of 4 pi. Still not enough. I go all the way around again, 6 pi. There we are. In other words, the angle 6 pi actually goes all the way around the circle 3 whole times, but ends up exactly pointing straight to the right. So if I'm on the unit circle x squared plus y squared equals 1, I've gone starting from the x-axis, starting from pointing directly to the right, I went around 3 entire times, 2 pi per rotation, so 6 pi angle is actually 3 complete rotations. I'm pointing directly to the right again. What are the coordinates of this point right there? Well, it's just 1, 0. So the cosine of 6 pi is the x-coordinate that this point pointed to, which was 1. So the cosine of 6 pi is exactly 1. A very similar problem, find the tangent of 6 pi. Okay, well, we just found that 6 pi is the angle where you go all the way around the circle exactly 3 times to return to the same angle you started with, pointing at 1, 0. The tangent of 6 pi is therefore the ratio of y over x. The y coordinate is 0, the x coordinate is 1, and 0 over 1 is 0. No calculator needed. The tangent of 6 pi is 0. Incidentally, if you type into your calculator tangent of 6 pi and it doesn't tell you 0, that's because you were in degrees mode, not radians. And remember, if an angle does not have a degree symbol on it, it is a radian measure. Moving on. Find the exact value for sine of 45 degrees plus cosine of 30 degrees. Okay, so in our unit circle, I have an angle of 45 degrees, and I also have an angle, let me use a different color, of 30 degrees. So if I label this point right here, the x-coordinate of this point is the cosine of 30 degrees, and the y-coordinate of this point is the sine of 30 degrees. Similarly, if I label this point here, this is on the circle of radius 1, of course, the x-coordinate of this red point is exactly the cosine of 45 degrees, and the y-coordinate is the sine of 45 degrees. So what I need to do is I need to determine exactly the value of the y-coordinate of this point and also the x-coordinate of this point. Now 30 and 45 degrees are angles that we can actually work with. So I'm going to draw this red triangle right here, just bigger on the right-hand side. So notice I've made it a right triangle. This angle right here is exactly 45 degrees. This width of the triangle is the x-coordinate of that point. It's how far to the right from the origin I had to move in order to get to that point. So this width is exactly the cosine of 45 degrees, and this height is exactly the sine of 45 degrees. Now looking at this triangle, the angles of a triangle must add up to 180 degrees. So a right angle is 90 degrees, this angle is 45 degrees. So let's call this angle right here t. So what I know is 45 degrees plus t plus 90 degrees must equal 180 degrees. Subtracting 45 and subtracting 90 from both sides, I get that t is 45 degrees. So this angle right here is 45 degrees. Lo and behold, I have this angle and this angle are equal. This is an isosceles triangle, which means this width and this height are equal. So we've just determined that the cosine of 45 degrees must equal the sine of 45 degrees. This is the x-coordinate of this point on the unit circle. This is the y-coordinate on this point. But on the unit circle, x squared plus y squared equals 1. Therefore, the cosine of 45 degrees squared plus the sine of 45 degrees squared must equal 1. X squared plus y squared equals 1. But we just observed that the cosine of 45 degrees and the sine of 45 degrees are equal because they are across from equal angles in an isosceles triangle. So since we want the sine of 45 degrees, this cosine of 45 degrees is equal to the sine of 45 degrees. Therefore, I have 2 times the sine of 45 degrees squared, and typically only when dealing with trigonometric functions, when we square them like this, instead of calling it sine of 45 degrees squared like I have over here, we tend to use the notation sine squared of 45 degrees. This is just a notational convenience, and it's really only used for trigonometric functions. Equals 1. Therefore, sine squared of 45 degrees equals 1/2. So the sine of 45 degrees is either plus or minus the square root of 1/2. In other words, it's plus or minus root 2 over 2. Now, how do I know which it is? Well, look back at our original unit circle. The sine of 45 degrees is the height of this circle. It's the y-coordinate, and in quadrant 1, y-coordinates are positive. So all of this is to say it is not plus or minus root 2 over 2, it is just the positive root 2 over 2. So I'm going to go ahead and mark up here in the upper left, we have just determined that the sine of 45 degrees is exactly root 2 over 2. Now we can turn our attention to that other triangle, the blue one, in order to find an exact value for the cosine of 30 degrees. Now the cosine of 30 degrees is going to be the x-coordinate of that blue point. Okay, we're going to use x squared plus y squared equals 1, certainly. But bear in mind that we're not going to end up with an isosceles triangle, so it's going to be slightly different, okay, from the computation of the sine of 45 degrees. So we're going to draw that blue circle. We're going to draw it, larger so that we can clearly mark it up. And we're not going to get an isosceles triangle, but we are going to get something we can work with. Okay, so let's draw reasonably accurately. Here is that triangle right there, if I was to draw this blue triangle. And observe that the x-coordinate is the width of this triangle, and that is cosine of 30 degrees. And the height of this triangle is the y-coordinate. That's going to be the sine of 30 degrees. Okay. Now the angles of a triangle must add up to 180. I've got 90 degrees here. I've got 30 degrees here. So what's missing is 60 degrees. So the little trick we're going to do is we're going to do a mirror image of this top half and reflect it down like this. So if I get another mirror image there, here I get 60 degrees and here I get 30 degrees. So look at what's happened. I've got 60 degrees, and if I stick these together to make one giant triangle, this is also 60 degrees, which means it's not just isosceles. It is in fact equilateral. So all sides must be of the same length. So what are the lengths of this big equilateral triangle? Well, the height of the original blue triangle was sine of 30, and this was just a reflection. So this is the same length, which means this right here is just 2 of them. Okay, that's important, but let's also look at the hypotenuse of the small blue triangle. The hypotenuse of the small blue triangle came from the hypotenuse here, but this is exactly a radius of the circle, and the radius of the circle is exactly 1. And since this big blue triangle is equilateral, all sides are the same length. So 2 sine 30 degrees is the same length as 1. In other words, the sine of 30 degrees is exactly 1/2. Unfortunately, we wanted the cosine of 30 degrees, so what we're going to do is we are once again going to use what's called the Pythagorean Identity, x squared plus y squared equals 1 on this unit circle. The y-coordinate is the sine of 30 degrees, but the cosine of 30 degrees, which is what we were after, is the x-coordinate. So the coordinates of this blue point are given by x and y, but on the circle x squared plus y squared equals 1. X is cosine of 30 degrees, so cos squared of 30 degrees plus y squared, that's sine squared of 30 degrees, must equal 1. Now, I don't know yet the value of the cosine of 30 degrees, but what I do know is that the sine of 30 degrees is exactly 1/2. 1/2 squared is 1/4. If I subtract 1/4 from both sides, we get cos squared of 30 degrees is equal to 3/4. Now I take the square root, and I say the cosine of 30 degrees is plus or minus the square root of 3/4. Once again, to distinguish whether I want plus or minus, I ask what quadrant am I in? In the first quadrant, cosine of 30 degrees, this x coordinate is positive. So I want the positive square root here, and I say the cosine of 30 degrees is positive root 3 over 2. So here we have root 3 over 2 as an exact value for the cosine of 30 degrees, which means, finally in the upper right, the sine of 45 degrees plus the cosine of 30 degrees is equal to, sine of 45 degrees was exactly root 2 over 2, cosine of 30 degrees was exactly root 3 over 2. I can combine these, they already have a common denominator, root 2 plus root 3 over 2. There is the exact value. And again, if you punch this into a calculator and it's not giving you exactly that, it's because you are accidentally in radians mode. These angles should be entered in degrees because they have the degrees sign. Moving on. Let's find an exact value for this expression. Okay. Pardon me. So here is our standard unit circle, x squared plus y squared equals 1. And again, I've got a 45-degree angle, that is important, and a 30-degree angle, that is important. However, we've already found, in the previous problem, the coordinates of these points. Okay, so this point right here had coordinates root 2 over 2, comma root 2 over 2. And this point right here had coordinates root 3 over 2, comma 1/2. Okay, we don't need to redo the work, we've already done it. Also, it's very common in just about any textbook or online, you can find a unit circle with a large quantity of standard angles already marked off. Typically what you'll find are 0, 30, 45, 60, 90 degrees in the first quadrant and similar angles in each other quadrant. And if you look that up and you find that, that's great. You can use it. In the previous problem, we saw exactly why certain angles are marked off at certain points. But now that we've seen how it works, we can just look that up. We don't have to redo all the work every time. So cosecant of 45 degrees times cotangent of 30 degrees. Cosecant is 1 over the y-coordinate. And when I say the y-coordinate, I mean the y-coordinate for 45 degrees. Cotangent is x over y. And here I mean the x and y corresponding to 30 degrees. So I look up the y-coordinate for the 45-degree point, and I get root 2 over 2. And when I look up the 30-degree point, for x, I see a value of root 3 over 2, and for y, I see a value of 1/2. Okay. Now we can simplify this if we want. I'm going to cancel off these common denominators of 2, leaving behind root 3 over root 2 over 2, or 2 root 3 over root 2, and if you don't want radicals in your denominator, this works out to be exactly root 6. Moving on. Find the exact values of the 6 trigonometric functions, again, sine, cosine, tangent, secant, cosecant, cotangent, of the given angle if they're defined. Sometimes they won't actually exist. Some of our trigonometric functions involve division, and if you try to divide by 0, you're going to have a problem. Okay. Axes, standard unit circle. Let's figure out what the angle 13 pi over 4 is. So observe that 13 pi over 4 is 8 pi over 4 plus 5 pi over 4. 8 pi over 4 is 2 pi. 5 pi over 4 is 4 pi over 4 plus pi over 4. So what I have is I have 2 pi plus pi over 4. The reason I've written it like this is so that we can come back to this circle and say, I want to start from the positive x-axis and start going around the circle in a counterclockwise motion. The angle I have to do is 13 pi over 4, but what's easier to count off is a 2 pi and then a pi and then a pi over 4. So a 2 pi is go all the way around, a pi is go halfway around, and then do pi over 4, which is 45 degrees. So go all the way around and then do another half rotation plus a 45-degree angle and end up there. Specifically, this angle is 45 degrees. We went all the way around and then went back around to get right here. So in quadrant 1, we know that a 45-degree angle points to root 2 over 2, comma root 2 over 2. I'm just taking the same x and y values, but reflecting them into the third quadrant. Okay, so it's the same general picture. If I were to draw, for example, this triangle here, 45, 45, 90, versus this triangle here, 45, 45, 90, they're the same triangle. They're congruent. They have the same angles and they have the same hypotenuse length of 1, a radius of the circle. So the coordinates of the points are the same, except they're in different quadrants. So while the lengths of the triangle sides are the same, but in different quadrants, that gives us different positive versus negative values. So I want the same coordinates fundamentally, but I need to make sure that in quadrant 3, both x and y are negative. So it's negative root 2 over 2, comma negative root 2 over 2. And now that we have figured out the coordinates of that point, we can come back and we can talk about the sine, cosine, tangent, secant, cosecant, cotangent of that angle. Because now we know where on the unit circle that angle points towards. Okay, it was really just the same as a 45-degree angle, but going all the way around the circle and then actually going into the third quadrant with it. So the sine of 13 pi over 4 is the y coordinate of that point, which is minus root 2 over 2. The cosine of 13 pi over 4 is the x coordinate of that point, which is also minus root 2 over 2. The tangent of 13 pi over 4 is the ratio of the y and x coordinates, negative root 2 over 2 over negative root 2 over 2, which simplifies down to just be 1. Then we have the secant of 13 pi over 4. That's 1 over the x coordinate, or 1 over negative root 2 over 2, which simplifies to negative 2 over root 2, or just negative root 2. The cosecant of 13 pi over 4 is 1 over the y coordinate. Since the y coordinate is the same as the x coordinate, this simplification is exactly the same. It's also negative root 2. And finally, the cotangent, I forgot my pi here, is, pardon me, is x over y, which is negative root 2 over 2. Over itself simplifies down to 1. All right, moving on, very similar. We want to find the 6 trigonometric functions of this angle here. First, we have to figure out where it's pointing. So 8 pi over 3 is 6 pi over 3 plus 2 pi over 3, aka 2 pi plus pi over 3. Plus 2 pi over 3. So I go all the way around, that's 2 pi, and then 2/3 pi is about here. Specifically, what's missing you could also view this, instead of 2/3 pi, you could consider it to be 1 pi minus pi over 3. So then what you could say is, I went all the way around 2 pi, another half rotation pi, but then I came back by pi over 3. So this angle right there is pi over 3, which is 60 degrees. Therefore, this angle right here is in fact 120 degrees, but since this is 90, that makes this 30 degrees. So I take my standard 30, 60, 90 triangle, which we did in another problem. I know this is 1/2, the hypotenuse is 1, this is root 3 over 2. But since I'm in quadrant 2, my x-coordinate is negative. So we're now back at this point where we have figured out the x and y coordinates of the point corresponding to the angle, which means we can go ahead and list out sine, cosine, etc., 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 which we will just breeze through fairly quickly now. So the sine of this angle is the y coordinate, which was √3/2. The cosine of this angle is the x coordinate, which was -1/2. The tangent of this angle is this ratio. I can cancel out the 2's, leaving behind -√3. The secant of the angle is 1 over the x coordinate, which is just -2. The cosecant of the angle is 1 over the y coordinate, which is 2 over √3, and if you're particular, you can call this 2√3/3. And finally, the cotangent of the angle is the ratio of x to y, which is just -1/2 to √3/2. Cancel out the 2's, -1 over √3, or if you are particular, -√3/3. There we have it. Again, -135, well, this is -90 degrees minus 45 degrees. So if I draw my standard unit circle, I have -90 degrees and then an additional 45. So if I put a 45-degree angle here, I've got that 45, 45, 90 triangle with side lengths √2/2, √2/2, and hypotenuse of 1. Since I'm in the third quadrant, both x and y are negative. So -√2/2, -√2/2. And here we go. The sine of -135 degrees is the y coordinate, -√2/2. The cosine of -135 degrees is the x coordinate, which is also -√2/2. Since the sine and cosine are the same, the x and y coordinate are the same, the tangent, which is y over x, is just going to be 1. It's worth noting that the cotangent is going to be x over y, but since those are the same, this is also 1. The cosecant of -135 degrees is 1 over the y coordinate, which simplifies down to -√2, and the secant of -135 degrees is just 1 over the x coordinate, which also simplifies to -√2. Okay, this is actually the same point on the circle from an earlier problem. In the earlier problem, the angle was found by, first of all, it was in radians. We also went all the way around the circle to come around like this, whereas in this problem, we just went that way, but ended up at the same place. Okay, charging forward. We are given a point. Notice that the point 8, -3 is not on the unit circle x squared plus y squared equals 1. 8 squared plus -3 squared is decidedly not equal to 1. However, what I can do, 8, -3 is in quadrant 4. It is outside the unit circle. But if I draw this line segment to find this angle theta, I can also make it correspond to a point on the unit circle here. Now, the coordinates of this point are exactly cosine of theta, sine of theta. The x coordinate is cosine, the y coordinate is sine, as long as this is the unit circle x squared plus y squared equals 1. But it's now going to be similar to the giant triangle. They are both right triangles with this angle of theta. So, let me switch colors. This x distance is exactly cosine theta. It's the x coordinate of this point. This height is sine of theta. This x distance is 8, and this y distance is -3. Since they are similar triangles, they have similar equal ratios. So the sine of theta over -3 is equal to the cosine of theta over 8. Or the cosine of theta is equal to -8/3 times the sine of theta, just by multiplying both sides above by 8. Then I'm going to look at this expression for this circle, x squared plus y squared equals 1. But for this particular point, x is cosine theta and y is sine theta. So cos squared theta plus sine squared theta equals 1. But we've just observed that the cosine of theta is negative 8/3 sine theta. Okay, so what we end up with is 64/9 sine squared theta plus sine squared theta equals 1. The common denominator here is 9. So what we have is we have 73/9 sine squared theta equals 1. Multiplying by 9 and dividing by 73, we can say, I'm going to take it back up to the top right here. That sine squared theta is 9/73. So the sine of theta is plus or minus the square root of 9/73, which is plus or minus 3√73/73. Now, how do I determine whether it's plus or minus? We just need to look at what quadrant we're in. Since we are in the fourth quadrant, this y coordinate is negative, so the sign is negative. So there is the sine of theta. Okay. Now that I have the sine of theta, I just need to remember, I accidentally erased it, but it's still preserved right here. The cosine of theta, we already observed, is equal to negative 8/3 times the sine of theta. So since I've already determined sine of theta is negative 3√73/73, we just end up with positive 8√73/73 once I cancel out those 3's and that minus sign. So there's my cosine of theta. And now that we have sine and cosine, we can start, in other words, we have the x and y coordinates of this point, we can find tangent, cosecant, etc. quite quickly. So the x for this point is cos theta is 8√73/73. The y coordinate, the sine, is negative 3√73. Negative 3√73/73, apologies. And now that I have both x and y, I can just start taking other ratios as follows. So the tangent of theta is y over x. We've determined the y to be negative 3√73/73 and the x to be 8√73/73. Lots of stuff cancels and I just get negative 3/8. The secant of theta is 1 over the x. I just need to reciprocate my cosine expression. 73 over 8√73, or √73/8. The cosecant of theta is 1 over the y, so I reciprocate my sine function to get negative 73 over 3√73, aka negative √73/3. And finally, the cotangent of theta is x over y, or cosine over sine, so 8√73/73 over negative 3√73/73. Lots and lots and lots of stuff cancels, and we just get negative 8/3. And there we have it. The real work was in finding the sine and cosine. Once you know those, everything else is fairly automatic. Okay, very similar problem. So -6, -7 is somewhere off in this quadrant. It is outside the unit circle. Apologies for my poor drawing. Here is my angle theta. The coordinates of this point are exactly cosine theta, sine theta. But because we have some similar triangles that we can construct, we know, for example, that cosine of theta to -6 is equal in ratio to sine of theta to -7. In other words, the cosine of theta is 6/7 times the sine of theta, just by multiplying both sides by -6. Now I turn my attention to cos squared theta plus sine squared theta equals 1 on the unit circle. This is true. Cosine of theta I replace with 6/7, so I get 36 sine squared theta over 49 plus sine squared theta equals 1. Common denominator is 49, so instead of sine squared, I'm going to call this 49 sine squared over 49. Let's see, 49 plus 36 is 85. So we have 85 sine squared theta over 49 is equal to 1. Sine squared theta is equal to 49 over 85. So the sine of theta is plus or minus the square root of 49 over 85, aka plus or minus 7 over root 85. If you prefer, plus or minus 7 root 85 over 85. Now, how do I know whether it's plus or minus? We look at what quadrant we are in. Since we are in the third quadrant, both of these should be negative. So the sine of theta is negative 7 root 85 over 85. The cosine of theta is just 6 over 7 times that. Sevens cancel out. So the cosine of theta is just negative 6 root 85 over 85. Okay, now that I have sine and cosine, we can, and remember sine is the x coordinate, sorry, sine is the y coordinate, cosine is the x coordinate. We can go ahead and we can construct all of the other trigonometric ratios in short order. So let me just clear out some space here, and then we will just hurriedly write down all 4 other trigonometric ratios. Once again, the real work was in finding sine and cosine, and now we're just going to go ahead and say the tangent of theta is the ratio of y to x, which is negative 7 root 85 over 85 over negative 6 root 85 over 85. 85s and their roots cancel out, negatives cancel, 7/6. The cosecant of theta is 1 over the y coordinate. I just have to reciprocate my sine function, negative 85 over 7 root 85, which is just negative root 85 over 7. The secant of theta is 1 over the x, reciprocate cosine, negative 85 over 6 root 85, in other words, negative root 85 over 6. And finally, cotangent of theta is just x over y, which is negative 6 root 85 over 85 over negative 7 root 85 over 85. Blah, 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 6/7. All right, word problem. So we have a cannon that's firing a projectile at an angle theta with initial speed v sub 0, often called v naught, N-A-U-G-H-T, v subscript naught, given by r of theta, which is the horizontal distance it has traveled, is given by v naught squared times the sine of 2 theta divided by g, where g is approximately 9.8 meters per second, and h of theta, the height that it has reached, is the maximum height that it reaches, is v naught squared sine of theta squared divided by 2g. So find the range and maximum height of a projectile fired at an angle of 65 degrees. So theta is 65 degrees with an initial speed of 300 meters per second. So v naught is 300. Well, the maximum range is just going to be given by 300 squared times the sine of 2 times 65 degrees divided by g, and g was given to be about 9.8. I'm omitting units here. This will all work out. So 300 squared is 9 followed by 4 zeros. Then I have the sine of 130 degrees over 9.8. Now, 130 degrees is not something that we can use a standard reference triangle to figure out, so you would just have to punch this into a calculator to get an approximation. Otherwise, this is about as far as you can go here. Similarly, h of theta is going to be given by v naught squared, so that's 300 squared, times the sine of 65 degrees squared over 2 times 9.8. And we end up with 90,000 sine squared of 65 degrees over 19.6. And again, since 65 degrees is not a standard reference angle, we can't really figure this out exactly. The best we could do is punch it into a calculator to get an approximation. Okay, the viewing angle of an object is how much angle in your eye the object forms. So it's related to the object's height and distance to the viewer through the formula. The tangent of theta over 2, where theta is the viewing angle, is equal to the object's height divided by twice the distance. So a forest ranger, here, views a tree that is 230 feet away with a viewing angle of 26 degrees. How tall is the tree? Okay. So we know that the tangent of theta over 2 is the height over twice the distance. The angle was given to be 26 degrees. The height we don't know, but the distance was exactly 230 feet. So the tangent of 13 degrees is h over 460. If I multiply both sides by 460, we get the height of the tree is 460 times the tangent of 13 degrees. And again, since this is not a standard reference angle, we're not going to get an exact answer. The exact answer is this, 460 times the tangent of 13 degrees. If you want to put it into a calculator, you will get an approximate solution. And in an engineering or science class, you might be expected to do so. In a math class, if you can give the exact answer, by all means, go ahead. If MyLab asks for two decimal points of approximation or something, then you have to go ahead and give the approximate answer. But most math professors would be just as happy to look at 460 times the tangent of 13 degrees and say that is 100% correct.